You are all welcome to this session of vector calculus, and in this session we are going to learn how to find line integrals of vector fields f, both in a 2-dimension and in 3-dimension. And so we learn from physics that when you have work is force applied to a particular this object which moves in a particular direction. And so we learned that force is always calculated as the work is calculated as the force times the distance. So let's take the elementary situation where we have on a smooth path like this, we have an object which moves from this point using a force F, let's say a force F, and on this horizontal distance, this object with the force being applied to it moves to this position. Let's say this position. Let's say this position is given as D or D. And so from physics we learned that the work done here will be, the work is equal to the force times the distance. And so this becomes elementary. Now we can have a situation where the same object moves on an horizontal surface, but in this case the force is applied in a certain angle. So if you have the same object and then the force is applied in this direction, and the object moves to this new position, then the distance we have D. You see that the object moved from this point A to point B, not by the force which is inclined, but we calculate the work done by the horizontal component of the force. So the force F, its horizontal component, is given as F, absolute value of F, times cos of the angle theta. And so in this situation, our work W is given by the force, which is the force which acts in the horizontal direction, in this case, which is magnitude of F cos theta times the distance that it traveled. Let's say the distance D is given by the vector D, and so the absolute value of D now becomes the distance. So in this case, if we rewrite it in another form, we're going to have absolute value of F, which is the force, times absolute value of the distance, which is D, times the cosine of the angle, this is theta. And from our earlier lectures, we realized that the definition of F times D, the magnitude of F times D times cos theta, is the same as the dot product. Remember the dot product that we learned. So we can write this one as the dot product of the force F and then the displacement or the distance. And so at this level, we realize that work done is a line integral, and it is being calculated using the dot product. In more complicated situations where we have, let's say, a plastic bottle which is floating on the sea or on a river, we can notice that the plastic bottle moves in an awkward direction. It is being moved by the waves of the sea or the river, and that force moves the plastic object in any direction. In such a situation, we can always find the work done in moving the plastic bottle from one destination to the other, when we know the current or the force of the sea wave or the river, what have you, the distance that it has moved. So to put it in a better way, this one can go up and say that the line integral the work done is always defined as the line integral of F, the force, dot the displacement. And then the distance that the object actually moves goes around a C, and we denote C as a path through which the object moves. That the object moves is C, and the F is the force being applied, dot the displacement. And so we can have a situation where the work done, if we decide to find the opposite of C, if now the object moves from, let's say, point A to point B, we can also reverse the path. So we can have a situation where we calculate the work done, this time from point B to point A. And so we can have the work done F dot dr from point C of the path C, that is now from point B to point A. And in most cases, what we do is that we negate the path. And so when we calculate the line integral, when we have reversed the path, then it's the same as the line integral of C F dot dr. And in this case, that is from point A to point B. But what happens is that since we have changed the path of the movement, this one becomes a minus. And so the line integral from point A to point B gives us a particular value. Now if we calculate the line integral from the final destination to the initial destination, which is from point A to point B, the answer is negative of from point A to point B. And another scenario is that if the object moves from point A, goes around in any direction, then comes back to the original point, how do we calculate the work done? And so we can have another scenario where the work done can be calculated as line integral of F dot dr, then the path of integration is C. But in this case, C is a path from point A to B to C and back to A. Where we have a situation like this, then we say that we find a line integral around a closed path. So we started from point A, went through other points, and eventually came back to point A. We said that we find a line integral around a closed path. And a closed path, the symbol for closed path is like this. So whenever we see an integral with this path, it means that we started from a point, went around in various dimensions, and then we came back to the original point. Another example is find the work around a circle or a triangle or a rectangle. That is, start from one point, go round, and then we come back. So that is how we calculate this in the line integral. So we'll take an example. First of all, we'll take an example where the vector field is on a plane, that is a 2-dimension. Then when we get used to it, then we can take another example where the line integral will be in space. So let's take the first example. So we have the line integral, which is, we denote it as the work done around a particular path, which is integral around the path of F dot dr. Now f, if it's two dimension, we know that f of x and y is defined as p of x and y I in the I direction plus q of x and y in the j direction. And then r also is defined in a certain parameter t. We use parameter t, and then it's also defined as x of t in the I direction plus y of t in the j direction. In this case, if you are using the parameterization, the parameter, then obviously t lies within a certain range. That is a and b, which means that a is the starting point of the parameter and b is the end of the parameter. And so we can also parameterize the force, which means that where we have f of x and y, we can also parameterize it and say f of r of t, which means that in this case, wherever we'll see x here, we'll put s of t, then y of t in the I direction, and then plus q r x of t, y of t in the j direction. And so if we are talking of two dimension that is working in a plane, then the work done with the line integral is defined as this. And so we can also, since r is defined in parameter t, we can also amend this one a bit. So integral c f dot dr, we can also make it integral f dot dr dt times dt. When we do this, you realize that it becomes easier because r is defined in t, and dr dt, we have not done anything to the formula because dt literally can actually cancel out. When they cancel out, then we still have our f dot actually dr. And so eventually, when we are working with parameters, then we can rewrite the formula of the line integral as f of r, the parameter t dot dr dt can be written in the shorter form, that is r prime of t times dt. And so when we are using parameters, this is how we're going to write the line integral, and it's in the form of integral along the path c, the f at r of t dot r prime of t dt. And when you express the line integral in this form, then life becomes very easy in calculating the line integral of a force, of a vector field or vector force. So we'll take an example, quickly we'll take as an example, we'll look at line integration or line integral in the plane. So let's take example 1, where we have find the line integral of f, which is in two dimensions, f of x and y, which is giving us xi plus x plus y in the j direction, giving the direction as r of t to be equal to t in the I direction plus t squared in the j direction, where t, the parameter t, is between 0 and 1. And so we take the solution. The solution will be like this. That's the integral of c f of r of t dot r prime of t dt. And so this is how we'll find the line integral of the given information. And so we know f of x and y to be equal to x in the I direction and then plus x plus y in the j direction. And so, and then r is also given as, r of t is given as t in the I direction plus t squared in the j direction. So with this information, we have to do the parametric equation for f of x. And so f at r at t will be equal to x. X is given as t in the r direction as t. So this one becomes ti plus x plus y. X plus y. X is t, then y is t squared. So this one will be t plus t squared in the j direction. So we can quickly put it in bracket form. So we have t for the I direction, then t plus t squared in the j direction. Now, we know r of t. So once we know r of t, which is given as this, we can find r prime of t. We can differentiate r respect to t. When we differentiate it, what do you get? We differentiate t respect to t in the I direction. That will give us 1. 1 times I is I. Then plus, if you differentiate t squared respect to t in the j direction, that will give us 2tj. So we can put it into bracket form. That will give us 1 and 2t. 1 and 2t. Now that we have parameterized f of x and y, we put it back into the line integration formula. And so that will give us integral of f of r of t. R of t will give us this value, which is t and t plus t squared. This one is the I direction, and this one is in the j direction. Dot r prime of t. R prime of t gives us 1 and 2t all times dt. And our t starts from 0, then ends at 1. So the next stage is to find the dot product of the integrand. Or we learned from the earlier videos how to calculate dot product of two vectors. And we know the dot product of two vectors will give us a scalar quantity. So let's carry on. We have integral from 0 to 1. And then we dot the I components. 1, t times 1, t times 1, plus this component times this, which is t plus t squared times 2t, right? And then that will give us the t. So the next is to open the bracket. Open the bracket, we're going to have integral from 0 to 1. Then we have t times 1, it gives us t. Then plus 2t times t will give us 2t squared. Plus 2t times t squared will give us 2t cubed, or dt. So we've put the line integral in the parameter t. So in this case, we're going to integrate t respect the integrand respect to t. So we do it term by term. And so if you integrate t respect to t, you get t squared over 2 plus the next step. If you integrate 2t squared respect to t, you get 2t cubed over 3 plus, if you integrate 2t cubed with respect to t, you get 2t raised to the power 4 over 4. And the limit is from 0 to 1. And so when we put the upper limit 1, we get 1 over 2 plus 1 squared is 1. We have 1 over 2 plus 2 over 3 times 1 cube. 1 cube will give us 1, 2 over 3 plus here 2 over 4. We can cancel 2 go into 2, 1, 2 go into 4, 2. So we're going to have t raised to power 1 raised to power 4 will give us 1. So we get 1 over 1 will give us 1. So we have 1 over 2. So finally we have 1 half plus half, that will give us 1. 1 plus 2 over 3, that will give us 5 over 3. So this is how we find the line integral, that is the work done by this force in the direction of r of t given as this. And so we have to recap, we have to parameterize the force using the values given, r of t, and that's exactly what we did. And we've been able to calculate the work done or the line integral to be 5 over 3. The next example, we are going to also look at line integral where the vector field is in space. And so the first example is an example where the vector field is on a plane x, y. We're going to take example 2 where the vector field is in space, that is made up of x, y, and z. So quickly we can take off this example 1 and then we'll look at example 2 quickly to do the line integration or line integral of a vector in space. So we take example 2, given f x, y, z, and is given as 3x squared y z squared in the I direction minus 2x x z squared plus 4 y x squared y. And so this is the vector field in space, and then the direction r of t is given as t in the I direction plus t squared in the j direction, plus t cubed in the k direction, where of course our parameter is located between 0 and 1. And so to solve this line integral in space, we still use the formula, that's the line integral C, where we have f of t dot r prime of t dt. And so we need to parameterize the vector field f. F is given as x, y, z, and it's equal to put it in the bracket form, so that we have 3x squared y z squared, and then in the j direction minus 2x z squared, and in the k direction we have 4x squared y, where we have r of t is given as t in the I direction, t squared in the j direction, and then t cubed in the k direction. And so with the parametric equation of r of t, we substitute it into f. So f now becomes f of r of t now becomes 3x. This corresponds with the x, this corresponds with the y, this corresponds with the z. So we have 3x, x squared, x is t, so t squared then times y. Y is what? T squared times t squared, then z. Then the z squared, z is t cubed. So t cubed squared, t cubed squared will give us t raised to the power 6. T to the power 6. This is the parametric part in the I direction. Then we come to the J direction where we have minus 2. X is t, S is t, then z is equal to t cubed. So t cubed all squared will give us t raised to the power 6. That completes the parameters for the J direction. Now we go to the K direction where we have 4. 4 times x. X is t. So x squared will give us t squared. T squared. Then times y. Y is t squared times t squared. T squared. So when we tidy up this one, what do we get? We're going to get 3 t squared times t squared times t raised to the power 6. That will give us t raised to the power 10. T raised to the power 10. That's for the I direction. And then for the J direction, we're going to have minus 2 t raised to the power 7. And then in the K direction, we're going to have t raised to the power 4. So that concludes our f of r of t. Now, we also know with r of t, we are going to find r prime of t. R prime of t. And that is differentiate this one with respect to t. So if you differentiate t with respect to t, you get 1. If you differentiate t squared with respect to t, you get 2t. And then if you differentiate t cubed with respect to t, you get 3t squared. And so we put this one into this formula, integral of f of r of t, and that gave us squared. That gives us 3 t raised to the power 10 minus 2 t raised to the power 7 t raised to the power 4 dot r prime of t. That will give us 1, 2, 2t, 3t squared, all the t. And our t starts from 0 and ends at 1. So now we do the dot product. So 3t10 dot 1 will give us 3t raised to the power 10. Then minus 2 times 2 is 4. 7 times t will give us t raised to the power 8. Then plus 3. T4 times T2 will give us T6, all the T. And then from 0 to 1. So if you integrate 10 by 10, we're going to have 3 10 raised to the power 11 over 11 minus 4 t raised to the power 9 over 9 plus 3 t raised to the power 7 over 7. And the limits are from 0 to 1. And so if you put the upper limit, you're going to have 1 raised to the power 11 is 3 over 11 minus 1 raised to the power 9 is 1 minus 4 over 9. And then 1 raised to 1 raised to the power 7 is 1 plus 3 over 7. And realize that if you put the lower limit, all the values becomes equal to 0. And so if you find the LCM component, that will give us the line integral of the vector field which is in space, which is given by the the components in the I direction, components in the J direction, and components in the K direction. And so that will conclude the line integral of vector fields. Whether the vector field is on a plane, we've seen an example 1, or whether the vector field is in space, that is what we've done example 2. And so given any vector field in a direction, we are now in the better position to find the line integral of the vector field. So thank you very much, and hope to see you when we do further line integrals in the next video. Have a nice day, and see you.